Hello everyone, my name is Evan here in Innovator, and today I'll be talking about my project on 60 pose estimation using RGBD images. Take this scene for example. There are a few objects here that we may be interested in picking up and performing some tasks with, but before we can do that we need to know exactly where they're located in space and how they're oriented. This is essentially the 60 pose estimation problem. I view this problem as having two different parts: instance identification and pose prediction. That is to say, given an input RGBD image, I need to first identify exactly where each instance of the objects of interest are, and then use that information to make pose estimations. For the first part, I train a mask RCNN instance segmentation model to identify each instance of an object as well as each pixel associated with that object. Using that information, I extract the mask point clouds for each object and look at a few different alternatives for pose estimation. I first look at conventional approaches, specifically fast global registration, RANSAC, and Super 4 BCS. I also look at a full deep learning based approach, which uses CNN to extract relevant features from the RGB image and a point net to extract relevant information from the mask point clouds. And I combine these using an attention pooling mechanism and finally make a prediction using an MLP. I also developed this iterative refinement network, which takes the previous network's predictions and iteratively improves upon it. To train these models, I look at two different datasets. One, a real-world dataset that is called LineMod. Here are a few pictures from this dataset. There's a few consistencies in this dataset that makes it easier for learning-based models to deal with. Given this consistency, I try to make a more challenging task for learning-based models by developing a new dataset. For my dataset, I throw a few objects on a table in Drake, and then pick a random arc to move a camera along and capture 20 images along this arc. Here are a few examples of what my dataset looks like. You can see the camera is not consistently positioned, and the scenes are highly cluttered, and sometimes objects are thrown on the ground. This makes it very difficult for learning-based models to handle this. Here are a few visual examples of how my model deals with the LineMod dataset. I won't even show you the results from the custom dataset because they do not look good at all. And in fact, it's not just my model that struggles with that dataset. Other state-of-the-art models also struggle with that dataset. Finally, I wanted to discuss some quantitative results. You can see that on the real-world dataset, hybrid approaches involving conventional algorithms perform very poorly, with the exception of Super 4 PCS performing relatively well. And when it comes to my data, the story is flipped, with learning-based approaches performing poorly compared to conventional approaches. But the only reason conventional approaches perform better here is that the data is captured with exact precision on the depth information. This makes it much easier for these algorithms to make pose predictions using the masked point clouds. However, this is not realistic and it would never happen in the real-world dataset, as you can see in the LineMod example. Another observation here is that my model is able to perform on par with the best state-of-the-art models out there. And finally, I wanted to discuss the practicality of each of these models. You can see that the GPU-accelerated learning-based models are able to perform practically real-time predictions, while the conventional approaches are much slower, and specifically the best performing conventional approach, Super 4 PCS, is 2 to 3 orders of magnitude slower than learning-based approaches, which makes it very impractical in real life, even though it is fairly accurate in comparison to other conventional approaches. Given this, learning-based approaches seem to be the most promising approach. However, they are limited in the extent of complexity in the dataset, and they should be improved to generalize better to bigger tasks with more difficulty. Thank you for watching.